Camera's going to be there, or should I go up top? Go up back. Wow. From undergrad to first time up on the lectern. This is great. So thank you everyone for joining us. We have up first this morning, Aspuru-Guzic, who is at the University of Toronto, Canada. He is professor of chemistry and computer science at the University of Toronto and is also the Canada 150 Research Chair in Theoretical Chemistry and a Canada CFAR AI Chair at the Vector Institute. He's a CFAR Lebovic Fellow in the Biologically Inspired Solar Energy Program. And Alon also holds a Google Industrial Research Chair in Quantum Computing. Alon is the director of the Acceleration Consortium, a University of Toronto-based strategic initiative that aims to gather researchers from industry, government, and academia around the pre-competitive research topics related to the lab of the future. Alon began his independent career at Harvard University in 2006 and was a full professor at Harvard University from 2013 to 2018. He received his Bachelor of Science from the National Autonomous University of Mexico in 1999 and obtained a PhD from the University of California, Berkeley in 2004, where he was also a postdoctoral fellow from 2005 to 2006. Alon conducts research in the interfaces of quantum information, chemistry, machine learning, and chemistry. He was a pioneer and important for today in the development of algorithms and experimental implementations of quantum computers and quantum simulators dedicated to chemical systems. I'll make a side note there. We heard a lot about VQE yesterday. Well, that was his lab that brought that to us. He's worked on molecular representations and generative models for automatic learning of molecular properties. And currently Alon is interested in automation and autonomous chemical laboratories, something that we also heard in Professor Vazirani's speech and some other people's talks as well. Among other recognitions, he received the Google Focused Award for Quantum Computing, the Sloan Research Fellowship, the Camille and Henry Dreyfus Teacher Scholar Award, and was selected as one of the best innovators under the age of 35 by the MIT Technology Review. He is a member of the American Physical Society and an elected member of the American Association for the Advancement of Science, and received the Early Career Award in Theoretical Chemistry from the American Chemical Society. He's also my co-founder at Zapata Computing and my partner in crime as the Chief Scientific Officer of Zapata Computing. So with that, I yield to my partner in crime here, Alon.
Thank you, Christopher. It's an honor to be there. If the internet gets broken or something, just let me know. I want to start my timer. And the only thing I would say also is that I share that MIT Technology Review recognition with Christopher himself, which is really an extraordinary scientist and lawyer and has a huge career. So it's an honor to be introduced by Christopher, and I congratulate you or I and him on this new program, and I really wanted to be there. So let me share my screen and let me just begin the journey of this talk, okay? So this talk has this title, right? What to do with a near-term quantum computer. It's a general talk. I will focus on simulation, but I also want to touch on basically the journey that we are right now on the variational quantum Eigensolver and in general, several variational algorithms. So I always like to begin my quantum computing talk reminding us how wise are humans. I just remember reading an article right now about a person that was found, I think 3,500 years ago or so, I recall, had cheese on their stomach and you know, like this really blue cheese. So we were more advanced than we kind of remember. And this is an example. This is a classical simulator of the motion of the planets and the motion of the stars, and even predicting the next Olympiad 2,200 years ago or so. Was found in the bottom of the ocean. And the reason that's important is because we wanted to simulate the classical motion of stars with classical devices. So let's fast forward about 2,000 years to the birth of computing. This book by Peter Gallison is a very important historical account of the beginning of the field of computer simulation. And the field of computer simulation is a hybrid between computer science, what was computer science at the time, computer engineering, and science. And surprisingly, obviously, this field has evolved tremendously. And now we have platforms such as PyTorch or JAX or TensorFlow that do machine learning, or systems like Zapata's own Orchestra or our own group's Tequila that allow you to do quantum computing at a very high level. But the journey started, with the early simulations of Enrico Fermi and Stan Ulam and Johnny von Neumann, where really some of the first simulations were about the structure of molecules, actually, in the early computer called MANIAC in Los Alamos. But this is the actual phrase that I really like about this book. Without computer simulation, the reality that it basically surrounds us will not exist. Apple just released yesterday the M1 Pro, this amazing chip with billions of transistors. It was designed by a computer, so it could not exist without a computer. So we've come back to designing chips at the end of this talk, actually. So just remember the fact that the chip on the new Mac that probably all of us already back ordered in the Apple website was designed by a computer, and without it, I could not be able to give you this talk and so on. So that's the importance of simulation, and simulation obviously has enabled our economy. It's almost impossible to imagine how many billions of dollars of wealth, even trillions, have been created by simulation. So now this is a historical kind of picture. I mean, this guy kind of a little bit looks like me. He's the advisor of my postdoctoral advisor. Okay, his name is Samuel F. Boyce. And when you see there is another one of these early computers, this is the EDSAC, the British equivalent of the MANIAC. It's kind of funny how the computers had much cooler names back then than now. So this is actually something that his student, John Popple, winner of the Nobel Prize, with Nick Handy and Isai Shabet, wrote about him. He wrote the first general program for simulating molecules. And this is what it says, right? It's very prescient quote, because I think if you reinterpret this quote in the modern context, this quote could be employed for thinking about asking Google a question about chemistry or natural language processing or other types of tasks that are much more modern. But at the time, what we really meant is basically, given any Hamiltonian or any energy function for a molecular system or a material system, can we get a molecular property? And in some sense, this is kind of like an oracle for chemistry. So let's fast forward to Richard Feynman. This is his paper in 1982 of simulating physics with computers, his multi-sided paper. And in that paper, he actually proposed how to simulate matter and actually how to start the journey of quantum computing. Notice how also we have gone down in terms of the names of computers. IBM computers are named after cities, which is kind of more boring than MANIAC or ENIAC. And also the Apple ads have become kind of crappier. Look at this beautiful Apple ad, and now look at this one. So what is the way of quantum simulation? It's the idea that you map a quantum system to a quantum model, time-independent, time-dependent Schrodinger equation, open, closed quantum system, etc. It could be a molecule, it could be other things, as I'll tell you in this talk. And then you extract a polynomially scaling amount of information from it. You will, for example, extract an energy in this case, for example. Or you could extract a molecular electron density or a reduced density matrix or a dipole moment. You cannot extract the full wave function of the system. That will require an exponentially scaling number of measurements, but nobody really can inspect the entire wave function of a system. So this is a plot done by the student of John Popple, my postdoc advisor, Martin K. Gordon, back in 2008. Okay, so this is a 13-year-old plot that actually still holds. Okay, so I still show it in my talks because it tells you the polynomial scaling of different methods, and it tells you why, I guess, Christopher and I still consider material science and chemistry as one of the powerful applications of quantum computers, because the exact simulation, which is what quantum computers promise to do, doesn't even make a dent as we grow supercomputers, right? Basically, it's a flat thing. And even by the time the grandchildren or my grandchildren die, we won't be able to simulate, say, 10 or 20 atoms exactly within a reasonable basis set. Whereas these other methods that are polynomially scaling actually, well, of course, keep improving, but they have their failures, okay? So exact simulation by quantum computers will allow us to have predictive rather than explanatory simulation of matter. That's what we started working on very early on and could still continue working on. And a quantum advantage, I don't know what's exactly going to be the term that people are using now, but it is something that we really think about a lot in Zapata computing and in my group. When a quantum computer outperforms a classical computer at a practical task, and this is the next speaker's definition of it. I mean, Christopher is a visionary on this space, and what he says is, I don't care if it's a heuristical advantage, a power advantage, a convenience advantage. Whenever an industrial process has a task that has been replaced by routinely running a quantum computer, we enter a new era. Okay, and then advertising our company, that's one of the missions of Zapata. We want to be the first ones in the world that do that. Okay, so, but the journey for me started in 2005. This is a plot from that time. I mean, literally, we were using the so-called phase estimation algorithm that was adapted from Peter Shor's factoring algorithm by Seth Lloyd to simulate many body systems. And what I did together with Martin, Peter Lott, which is a scientific advisor for Zapata as well, and Tony Dutoy, very important, this is co-authorship. What we did is basically take that algorithm and kind of adapt it to the time evolution of a molecule instead, and work out the details of how long it would take to simulate a molecule like cholesterol, which probably requires the same number of qubits as factoring a number. So in the long-term error-corrected regime, algorithms like this one will be king and will be very important in terms of simulating matter exactly. Just not only the electronic structure, we have worked out the dynamics, we have worked out subsystem simulation. And when I say we, of course, a lot of it is my group, but also several other groups around the world. So what is NISK? I mean, you heard a lot in this conference, and NISK is kind of like this intermediate regime between the classical simulation and the quantum computer. It is a very, I like this plot because it really is like a Verdant plane, but with a lot of opportunity and of course a lot of challenge. And these optimizations here, perhaps adding finance, are still, this is a Rigetti plot, but are still kind of like some of the things that we think about in my group and also at Zapata. Okay, so chemistry optimization, machine learning, finance are some of the things that companies are thinking about, natural language processing. So you might say, well, Alan, how is the field going? I mean, you, in some sense, as I'll tell you, my group was one of the groups that started NISK because we developed by Jared McLean leading this with Van Hong-Jung in my lab, the variation in quantum Eigensolver. But obviously, we really cannot keep up with the literature, and you can actually see that by the fact that 2019, 2020, and 2021, I have put out a review paper. This review paper is very dear to my heart. Most of the co-founders of Zapata Computing are here. Then this paper, I was a co-author also with the British team of Simon Benjamin. And then in this one, this is mostly my team, but also some Zapata colleagues and also Singapore colleagues. In these two, of course, we were taking a chemistry view of what quantum chemistry in a quantum computer would look like. This is a physics view. There are complementary articles. And then in this one, we're really trying to take the big challenge of trying to survey all the NISK algorithms, okay? And hence the title of this talk, What to Do with a Near-Term Quantum Computer. And this is now not to overwhelm you, but let's look at that, right? So again, the variational Eigensolver was covered in this talk already. This is perhaps the seminal paper in the sense that it did the first scalable implementation in the Google computer. This was led by Jared McLean and Ryan Babush in my lab with Cornelius. Sorry, yeah, Jared McLean and Ryan Babush. But this was probably one of the first applications of the Google quantum computer. I love this paper because it also shows the phase estimation algorithm together. Okay, the first algorithm that we proposed in 2005, QAOA, a cornerstone of this, and also a couple other papers like the variational quantum generators and autoencoders that also my lab pioneered. And notice that a lot of these algorithms minimize or maximize something. That's where the connection between chemistry and machine learning and optimization comes along. There is a loss function that is optimized using the quantum computer. I'll come back to details. So the NISQ algorithms, look at this. These are all the algorithms related to simulation. BQE and related solvers, excited states, simulation of Hamiltonians, including thermal states, open quantum systems, preparing states, our own quantum autoencoder work, as well as others. And then I'll tell you at the end of this talk about quantum computer aided design, which is for us a big application, inspired by the quote that I told you about. But what you want to see here, and it's the most important thing, is why we had to write the review paper. Count the number of 2009s, 2019s, and 2020s in this paper. Okay, it's incredible, the explosion in algorithms and the explosion in ideas for quantum computing. That's why you had this conference. That's why you're creating this masters, I think, as well, given the timeliness of the incredible growth of what's happening in this field. Now, continue and you go to machine learning. The own quantum circuit-borne machines, one of the super powerful applications of Zapata computing, the quantum GANs, very important, quantum reinforcement learning, etc. So variational quantum classifiers, all sorts of different applications for quantum machine learning. And then, of course, combinatorial optimization problems are actually quite important. Numerical solvers, I think more and more the quantum computer will become like a little auxiliary computer that allow you to do factoring, solving linear systems of equations. A lot of work as well at that on our company and my group. And finally, stay tuned for really cool work that's going to come out on finance. Okay, I'm not even going to tell you who's going to bring it out, but you can imagine extremely cool work on finance as well coming up. And finally, there are unclassifiable other applications. For example, error correction. This is an early paper led by Peter Johnson, also a co-founder of Zapata Computing. Schmidt decomposition by Carlos Bravo, Prieto, etc. So these are a lot of different really cool applications from different groups. And my group has committed to actually make a live website where we can continue adding papers. So we don't have to write a review paper every 6 months and every 3 months and then like that, But it was very important for my group to write this paper to actually just catch up. So I recommend you to read it. So now let's just discuss a little bit the variational Eigensolver at a high level. What it's all about is, and I know my next speaker and introducer is a musician. So let's think about music. Let's think about tuning a guitar. Every time you strum the guitar, it's kind of like asking the quantum computer to give you a quantum state, like trum, right? That will be the quantum state. And the parameters of the guitar will be, the tuning parameters. And those will be the state preparation quantum gates, okay? That will actually create that ultimate wave that comes out of the instrument. It's quite similar because what comes out here is basically a quantum superposition over many different states. So not dissimilar to the wave that will come out of a string that has interference between all the different strings, okay? So it's not such a bad analogy of thinking of a variational Eigensolver or any variational algorithm, for that matter, as a guitar that is being tuned. And the idea is that you tune it against something. In the case of molecular simulation, we use probably one of the most fundamental ideas of quantum mechanics, the variational principle, that allows us to then minimize the energy and update the parameters. And the art of variational quantum algorithms is to think about what is the ansatz that you prepare, think about how to minimize the number of measurements, think about what is the objective function. And those will be, and of course, the mapping. All of those things will be the things that people are making progress day to day in the field, in the archive. So again, in our early paper of variational Eigensolver, we introduced the word QPU, now used readily. We also say something that is very important that many people don't say. My idea of the future is, of course, quantum computers will be parallel. There will be rooms full of them. There will not be one quantum computer, but if you want to do variational algorithms, you can imagine a room with 1,000 quantum processors, right? Or something like that. I don't see why this is not going to happen in the near future. So therefore, when you see a timing, even from the papers that we publish from Zapata and my group that says this is going to take 72 days, in variational algorithms, that means 72 quantum computers could be in a room, and then that will take you 1 day, okay? So there is no limit here because you can use several quantum modules to get different expectation values of different operators, or even all of them to accelerate the expectation value of one operator. So that's very important, and it just lost in the literature that we have this parallelism for variational algorithms. Obviously, each module has to be big enough to store the wave function that you want. So if you want to have a 200 qubit module, you have to have 200 qubits in each one of them. But the point is, if you can actually build that, then humanity is not stopped by making a room full of quantum computers that will allow you to do variational algorithms. And again, the classical computer will just carry out the operations outside to optimize, get gradients, etc. So this is where everything that is done under the hood of VQE could have been the subject of a talk, but now it's so black boxy that that's the point of what I'm going to make, right? The generation of Hermitian operators, circuits from unitaries, fermion operators, variational optimization, all of that is super automated. Academic groups, industry groups are working on all of these different aspects: ecstatic states measurement, reduction, unitary coupled cluster methods, ansatz optimization, etc. I want to emphasize the work of my colleague Artur Ismailov and many others, including, of course, people at Riverlane or Google or of course, Zapata Computing. But the record holder at the moment is Artur, okay, that has reduced the number of measurements required for a quantum computer to n to the 1.4 from n to the 4, which was the original algorithm. I had huge quote unquote academic fights with our Microsoft colleagues that were very pessimistic about this, Matthias Troyer and company. And it's funny how in some sense they don't make any noise about this anymore because this is all kind of a solved problem. Okay, so I like when basically silently wins these battles. This is our package developed in my lab, integrated with the tools like Orchestra from Zapata. But this package is called Tequila. That was the original name of my first quantum computing package with Tori Dutoy. So we just revived the name. This is basically the brainchild of Jacob Gottman, Somner, Tere, Alba, Cyril, and many in my group, as well as Artur's group nowadays. We develop it with many other contributions from around the world. So Tequila is just incredible. It's already published, by the way. It says impressor, but I apologize. Tequila is extremely high level. What you write here in the blackboard here is literally this code, nothing else. And this code will allow you to optimize a variational wave function. Okay. So I haven't seen a package that is higher level for variational algorithms than Tequila. At least this is my opinion. For example, this is the code to simulate the benzene molecule. So how far have we won since 15 years ago when I started the journey of quantum simulation? It's incredible. Tequila allows us to actually try to implement all the variational algorithms in chemistry that are around the world in a really fast pace. So that's our goal. So if anybody in the room or in the YouTube streaming wants to contribute an algorithm, it will be a few lines of code of Tequila. So you could also take your ansatz, take your algorithm, and add it to Tequila. Tequila, of course, stands in the shoulders of giants, has a bunch of backend simulators, has a bunch of optimizers, and can run also directly on quantum computers. That's some of the work that we're doing. Runs on JAX and OpenFermion, and of course, quantum chemistry packages, and is integrated with Orchestra, which you can imagine it can orchestrate its running on several hundreds of thousands of iterations, and also store the data from it, etc. So what are the things that we've been doing this year in my lab or have been published that will allow you to actually reduce the number of qubits? I think one of the most important ones is this multi-resolution analysis, quantum Eigensolver. we noticed that I think that one of the biggest issues is if people use standard basis sets, they're kind of like wasting the resources of the qubits, because you can imagine doing the most sophisticated work in the classical computer, a grid-based analysis that with second-order perturbation theory allows you to build the best orbital set for a molecule that probably you can build, okay, with the madness code. Notice how that's also a cool name, by the way, the madness code of Nick Harrison, of Harrison, now at Stony Brook, that Jacob Korman was a developer in his PhD, to get these PNO orbitals that, you know, basically are plug-and-play replacements of the MOs people usually use. Then you can go back, do all the tricks that you can in the Hamiltonian representation, in the ansatz, in the variational algorithm. But this is kind of a plug-and-play replacement that it's basically connected to Tequila. That the reason is so important is because you can see the variational Eigensolver in the minimal basis, typical kind of benchmark for quantum chemistry, and the huge improvement that you get just by using the PNOs. This is the exact answer, right? Pretty much in black. And you can see the huge improvement that you get. And when you think about extrapolation to the exact answer, okay, how many qubit reductions you will get, our estimates are that for molecules like boron hydride, for example, you will get this factor of 4. For these molecules, maybe you get a factor of 5, some of them even factors of 10 or so. I mean, up to factors of 10, you can see here. Okay, but you know, factors of 5 to 8 or something, whatever is what you can get in this plot tells you this will give you the exact extrapolated infinite basis set solution of a problem with a very modest number of qubits. So MRABQE, I think, is here to stay, and that's what you should use if you want to map problems to quantum computers. And this is published already, by the way. This is the Metavariational quantum Eigensolver, led by Alba in my group. Now moved on to become an independent group member in Spain. What this does, it actually learns many states at once and combines quantum machine learning with quantum variational Eigensolver. So this piece is an encoding of a Hamiltonian that depends on many parameters lambda. And what you do then is learn the Hamiltonian with all the different parameters lambda together, okay? So that allows you to, for example, if the parameter is an intermolecular distance, feed it, say, 10 square hydrogen 4 molecules and learn the entire potential energy surface, because the wave function is parameterized with respect to all of these different points in the wave function. And also because you add this variational layer to the circuit here that encodes the wave function with respect to the parameters, you kind of meta-learn all the different points and lower the error as well. So it not only is better at learning all the parameters, all the wave function as a function of parameters at once, but also it allows you to have a better ansatz. So MetaVQE, I think here is also to stay, to simulate potential energy surfaces, bond dissociation, and of course, many body Hamiltonians for physics that also depend usually, for example, in an external parameter such as magnetization. So in MetaVQE and also the variational Eigensolver are here to stay. Now, this article, which by the way, this IP is of course being licensed by Zapara. It's a very important IP, generalized as well by Arthur Ismailov. But what we did with Jacob Kottmann here is find, if you want to think about it that way, an exponential improvement in the cost of calculating gradients for fermionic operators for chemistry. Okay, so we figured out how to think about the operators for many body systems spectrally, and therefore find constant cost 4 or 2 measurement operations, right, to calculate a fermionic gradient. Okay, this of course again has been extended by Arthur Ismailov. There is another beautiful work by our Xanadu colleagues where they took a different approach that I really like. They thought about generic quantum gates that could also be thought about fermionic rotations, and they also are able to calculate gradients efficiently. I think these two approaches are complementary, but our approach is, I think, physics inspired in terms of the many body operators, and you can see in red here the exact gradient and the how we can get it basically 100%, or you can even have approximations G plus and G minus. And remember, if you have a gradient, you don't care too much about perhaps its magnitude sometimes, but if you know exactly where it goes to zero, you can get it. So you could do this approximation to do the exact one, which only takes 4 measurements. So I believe also this gradient passing is going to be so important, not only for chemistry, but the generalization of Arthur Ismailov allows you to do machine learning applications as well. So analytical gradients in quantum chemistry are here to stay. So I show you 3 very important, in my opinion, contributions from my lab to this field this year. So I'm going to just breeze through some of the experimental aspects because I want to move to QCAD and end this talk with QCAD. Okay. So this is a paper I told you about, 2016. It looks so vintage, only 5 years old, but this was the pulses, the gate, the circuits, and the energy for the hydrogen molecule. Again, the variational Eigensolver, you can see the errors with respect to the exact in red. And you can see here the fact that because the gate circuits are longer, phase estimation has more error in the short-term quantum computers, but obviously will be the king algorithm for long-term quantum computing. Now you can see here 2018 progress. We worked with Cornelius Hempel in doing the variational Eigensolver for the lithium hydride molecule. Pretty fun paper to work on. Now we were optimizing 2 parameters, alpha and beta. Beautiful work by our IBM colleagues a little bit later, or contemporary, 7 qubits. It appeared in Nature. Very noisy at the time. Obviously now there are better qubits, but you can see here the better algorithms, but you can see here the beryllium hydride molecule in 7 qubits. And this is one of my dreams, a colored plot of superconductors where each one of the superconductors is an orbital. It's kind of one of my dreams, and it just was implemented here in this beautiful paper by the IBM team. Our colleagues at IonQ, company that just went public, did a 3-qubit simulation on a molecule, and of course AquTraps are an interesting technology to be watching. And the first time I saw this paper, I was like, wow, they used 20 qubits, and of course no, they only had used 3, but obviously I imagine them are still working very hard on higher big QEs. What state of the art, at least the largest experiment that I've seen so far, is 12 qubits, a hydrogen chain, very simple Hartree-Fock ansatz by the IBM colleagues. Use this kind of plaquette of their superconducting qubit machine. Some people criticize this paper. I find it a very good paper because it has very low errors. Okay, errors comparable to chemical accuracy. It produces the potential energy surface of the strongly correlated system with a very simple ansatz, obviously. But what is very nice about it is it tells you the state of the art. This is where we are. We have short circuits over about 12 qubits. So where are we going? This is a very important paper by Zapata Computing, led by Jerome, Jonathan, Max, and of course a collaboration and contributions from our colleagues at BP. This is a very good example of what industrial research can do. Tells you the number of days, the number of gates, the scaling with respect to the number of electrons that you require to get these molecules exactly. Now, it's funny how, of course, things go in parallel. One collaboration that we were just discussing in a launch in Toronto between Jacob Kotman and Zapata Computing and my group, and this kind of joint project is obviously to update these tables with the MRAVQE. So, I mean, this is the genius of having all the tools available. You have Orchestra from Zapata that can rerun these experiments, okay? We have Tequila that can really readily run MRAVQE, combined with all the developments that Zapata has proprietary and also public with respect to this project, will allow us to very soon reduce these costs. And this number of 13 qubits per electron, as I told you, could be reduced by a factor of 6 or so by MRAVQE. So this is the nature of the field. This paper that was in the archive last year is now kind of obsolete in some sense, but something that I really like about Zapata, it gives you, it's a company that gives you basically non-inflated, realistic estimates at the time of what's going on. And this is kind of our spirit and the spirit of my lab as well. So for the remainder of this talk, I want to go back to what I told you about the Apple chip. To simulate a quantum computer, you will need another quantum computer. Why is that? Okay, that is the new thing that we were working in my lab. Well, you heard the term quantum supremacy perhaps in this symposium already. Google and our Chinese colleagues have shown experiments that arguably have quantum computational supremacy. In other words, are better quantum computers than, they are better at a task sampling from a circuit than a classical counterpart. Okay, so the question that we have is, well, if those chips are already non-simulatable, that particular task by a classical computer, when will designing them will be hard? Because remember, one of the biggest applications of chips in terms of impact is simulating themselves. Okay, so to produce an ARM chip like the M1 Pro of Apple, you will need a classical computer, a supercomputer to do that. Well, so in this paper, which by the way also is already published, I really apologize, I didn't update all my references. I'll do that for my next talk. You see the following, right? So this is a number of qubits, number of transmodes as a function of year. I like this plot of our paper because it tells you that the number of transmodes in the device is indeed growing. And if you look at the roadmaps of IBM, for example, or others that have been published, they continue to increase the number of transmodes. It's not only important to increase the number of transmodes, as you know, we need to increase their fidelity, right? But also people are working on that. But having said so, if you actually look at the number of qubits that you can simulate with classical simulators, for example, even running in the IBM Summit, we estimated that this is the number of qubits you can simulate in a supercomputer, and this is the reason why supremacy happened, right? Because we have this gap here. So now the question that we had in our paper was, okay, what happens if we figure out how long will it take to simulate a transmode on a quantum computer in the VQE sense, or even in the quantum dynamics phase estimation sense? What is the wave function mapping to simulate a qubit with a qubit? And turns out, I mean, the technical details, of course, in this 40-minute talk, I cannot go over. I'll show you a few of them. We figured out, this is work led by the genius of Tihak Kiao in my lab, collaboration with former group members and leaders at Intel Quantum Computing, Gian Giacomo Garracci and Nico Sawaya, of course, collaborations with Will Oliver at MIT, and my student Tim Menke, and then Dylan Sim, which is now at Zapata. So anyway, this paper I really like because shows you here now the size of the quantum computers. And eventually here, there will be these quantum computers that will require to be simulated by a quantum computer. It is this regime. And notice our prediction, this will happen maybe next year, okay? So if everything holds in this extrapolation, the next year or the year after, we're in the regime that I'm talking to you about. This is how fast the field is moving. Okay, so future quantum computers will need to be designed by a quantum computer. So QCAD is one of the biggest productions, new products of my lab. Okay, so how do you simulate a transmode? You think about its Hamiltonian and convert its operators to spin operators. So this is kind of the kinds of things that we do in chemistry, but there was work that needed to be done. This is work led by Nico Sawaya. Also, we collaborated on this paper with him on these Hamming encodings for these bosonic systems that are the qubits, multi-level bosonic systems. So we use gray codes, okay, to encode the multi-level systems that are the qubits. So there's a lot of things under the hood that became papers on their own. This Nature Quantum Information paper, for example. But ultimately, what we have then is a way of mapping these kind of Hamiltonians that for the qubits into actual spin terms, okay, that then can be simulated by any kind of variation of quantum Eigensolver for the ground, for the excited state, and for quantum dynamics. In this case, for quantum dynamics, you could do it with Eigensolvers or also with phase estimation. So in this particular case, we use fully connected ion traps as an example, which is pretty nice because that will mean that an ion trap will be used to simulate a superconducting qubit. That would be kind of a cool experiment to run. An ion Q to simulate an IBM or a computer. That would be an interesting paper to publish in terms of just what you can do with that. But you can imagine here these 4 qubit ansatz used to simulate this transmode physical qubit. And we did the ground state with the VQE and the excited states by the so-called variational quantum deflation algorithm. Here is the energy levels, right? Within the equivalent of chemical accuracy. I mean, this is where Will Oliver joined us, right? Will basically told us, I mean, I need to have errors within 10 megahertz. So therefore, here we are. This is a 4-qubit simulation. To get this paper published, we need to get past reviewer number 3, whoever it was, or number 4. They wanted us to do larger number of qubits. So the final version of this paper, and I don't have the plot here, but the final version of this paper also contains what I think is the largest variational quantum Eigensolver simulation ever published, with all optimization of parameters, which was on 16 qubits. Thank you, reviewer, for delaying my paper for a year, for trying to make us do acrobatics numerically. But anyway, it helps my group become better at numerics and better at scaling this up. But at the same time, just highlights, in some sense, the toxicity of the quantum literature. People just asking kind of, I think, silly things to do, because that's just making us jump for another hoop. So anyway, sorry for criticizing my reviewer, but I found that kind of not useful. Another thing that we did in QCAD, obviously, is can we simulate this boson sampling or other quantum optics experiments with quantum computers? Series of papers that I don't have time to explain to you right now, but we have a big trend in my lab of trying to design quantum optics experiments with quantum computers. A simple example that connects with this one is finding the quantum circuits that do all the quantum optical setups. This will be very important if you want a quantum computer to simulate, say, PsiQuantums or Xanadu's computers. For that, then you could imagine having a digital circuit, and we have here the mappings for those digital circuits, and then using those digital circuits to, for example, simulate boson sampling. So if you wanted, say, to understand what will happen in the Chinese recent boson sampling experiment using a superconductor, this paper of ours allows you to actually do that. Again, it was already published. So now coming back, because I need to end now, what is the roadmap? I have 2 minutes left to leave 5 minutes for questions. If you look at the roadmap of the future, this is an old paper from 2015 from Lili Mook, which, by the way, is funny. She actually left Nature Chemistry, and now she works at Riverlane, actually. So it's interesting how she wrote this paper, kind of critical of quantum chemical advantage. But you can see here some of the early players in the field. Here is our competition that we had around this time with Microsoft. But here you can see kind of like the prediction of when these things will happen. I still believe these numbers are not that off. And why am I so excited is because you can see here all the different number of qubits and the sophistication of the hardware as you move along in this journey. Look at the first experiment we did with Andrew White. I don't even talk about it anymore. Our first quantum optical simulation of a molecule in an optical table. This was 2 qubits, 4 qubits, 2 qubits again, 7 qubits, 12 qubits, right? And again, this is a map of IBM. You can see them promising to us 400 qubits next year. That will be an interesting system to play with. And I think the future is to come. So with that, I'm going to show you a Zoom-like picture of my research group. Here they are in their physically distanced type of pictures that we took last year. And our first retreat, all of us vaccinated. Half of us are here, but vaccinated and in Northern Ontario. And I really want to thank in this group some of my quantum group members. Tiha here, incredible person. Jacob Gottman, Chong, she's just incredible in quantum computing. And then let me see who else I really want to emphasize. Lasse Jansen is working on very, very cool stuff that will come out very soon. Of course, Avinav Anand and Philippe Jensen, very, very, very great graduate students that work on this. And then Sumner is not there, but also critical. And on that note, I'm going to open up for 5 minutes of questions, I guess I have. And I really thank you for your attention. And I look forward to the Q&A. Thank you.
Thank you. Okay, do we have any questions from the audience here live?
I don't bite.
We do have some online. One from Catherine. Let's see.
You want to read it?
This is where I need my glasses. Okay. Let's see. Alon, great talk. Are you planning to add time dependence to your package in order to calculate the real-time dynamics of matter beyond calculating just the potential energies?
Very good question. I don't know if the time-dependent simulations that we did for the QCAD paper are fully implemented in Tequila or if they were done by the Intel team independently. I think it's the latter. But definitely we could do it, or if the questionnaire is interested, we can certainly do a hackathon with the questionnaire or anybody and add them to Tequila. Just yesterday, we were having a conversation about adding, embedding methods and DFT, long-range corrections and other things to Tequila in a hackathon of 2 days with a collaborator from McGill. So if anybody wants to add things to Tequila, let us know, and especially write to me and Jacob, and we can fly you to Toronto. We can sit down in 2 days and add a feature like this.
Anyone else? One last provocative question from me. What is your ultimate dream in the area of chemistry with quantum computers? Let's put this on, say, a 10-year, 20-year horizon. Okay, let's pretend we have that magical fault-tolerant computer with a gazillion qubits. What
Christopher, I love that, because you probably saw in Twitter a picture of your team when they visited Toronto. Zapata Computing has an office in Toronto that is ever growing and an office in Boston, and the flight is only 1 hour different, 1 hour away. So we executed our first flight post-COVID recently. 5 of the Zapata team came, met with our Toronto team. But I did something very special to me, actually very emotional. It was a very emotional moment because I have 2 missions in my life. One of them is to use AI and robotics to automate the laboratory of the future. I, of course, believe quantum computing will be a piece of that, which is part of the answer to you. But what was really cool is that I took the Zapata Computing people on a tour of my crazy robot that does chemistry and like has, liquid handlers and so on. And it's kind of what the other startup I co-founded, Kebotics, which is also in a very good path as well, is doing. And I believe 10 to 15 years from now, the unification of those two kind of might seem to use schizophrenic parts of my life will happen. And we will have an integrated quantum computing AI robotics lab that will be printing molecules in the future, enabling what I like to call the era of molecules on demand. Do you want a perfume? Print it. Do you want to design a new molecule that does a new display or a new catalyst? You will just design it, print it, and test it, and therefore accelerate the scientific discovery. That's the ultimate mission I want to kind of accomplish in the arc of my scientific career, if I can. Of course, it will take this decade or so or more of work or whatever it's going to take. Finally, I like to say, and probably you will address in your talk, there are other applications of quantum computers that could potentially come in, and many of them will benefit humanity as well, such as logistics. So I see the future of a future where now the quantum computers will really start making a dent, helping humanity. And if that happens, the same way computers help humanity, we will have accomplished something together as a community, and of course, as a team, you and I, Christopher. So that's kind of my vision of where we're headed, and the dream of what a quantum computer could do in designing materials.
And any last parting messages? We're starting a 4+1 master's program. If you were an 18-year-old kid thinking about this, what would your message be to those students today thinking about this field?
I would say it's funny because at Toronto, we're starting a master's program on AI for materials. Okay, first thing is like minds think alike. So of course you or I already have beat us to the punch in quantum computing. So congratulations. But I'm creating a similar one. I do believe strongly that these master's programs will allow us to create a quantum industry. If you're a kid that wants to kind of enter the field really quickly, I think a good path will be do this master's program and then join a company, and then maybe you go back to your PhD later if you really like this, or maybe you stay in the company and do some work. But if the explosion that we see, I mean, the QCAD paper that I showed you, those plots about when a quantum computer will be needed to design another quantum computer, suggest that there will be a job as a quantum circuit engineer, right? As engineer of quantum computing circuits. Let's just imagine that's a job in the future. being trained with a master soon will allow you to enter that market as soon as possible. So to the younglings, there's so much resources. There are open source packages. Tequila has a bunch of tutorials. There are internships at Zapata, internships in my own group. MyTax is a huge opportunity for you guys to come to Canada to research with me. So any URI undergraduate that wants to say, I want to spend a summer, and summers are great in Toronto, by the way, so they're not as cold, so come in the summer. Welcome to have you apply. And because I know this is Christopher's alma mater, I actually make a promise that the top URI undergrad that applies next summer will apply with me for a MyTax, at least one. So this is a promise that I'm making virtually. So I would love to have at least one applicant from URI to come in the summer to my lab.
Well, thank you, Alon. We appreciate you taking the time. And next year here, hopefully.
Well, looking forward to listening to your talk. And if anybody wants to send me a message, the best way to do it is send me a Twitter direct message. I barely read my email, so that will be the best way for me to communicate with anybody in the audience. Thank you very much for your time, and I look forward to listening to Christopher's talk and the rest of the program today. Thank you.
So back to the lectern again, and this is the second time I get to introduce this distinguished professor. This time a little bit shorter version. Dr. Vazirani is the Roger A. Stouch Professor of the ECS and the co-director of the Berkeley Quantum Computation Center. Dr. Vazirani is one of the founders of quantum computing. That's not an exaggeration by any means. He's the author of An Introduction to Computational Learning Theory with Michael Cairns and Algorithms with Algorithms, the book Algorithms, with Sanjoy Dasgupta and Christos Papadimitriou. Umesh was inducted as a fellow of the Association for Computing Machinery in 2005 for his contributions to theoretical computer science and quantum computation. And in 2012, he was awarded the Fulkerson Prize for his work on approximation ratio for graph separators and related problems. And he was elected to the National Academy of Sciences in 2018, really one of the founders of the very field that this conference has its theme around. So a warm welcome for Professor Vazirani. Thank you.
Great. Thank you so much for the very kind introduction. Let me share my screen so we can get well, let's see what's going on here. Sorry, I hope this is okay. All right, so my what I'll talk about is this kind of cryptographic leash for quantum computers, classical proofs of quantumness. So this is actually let me start. So this is these are techniques for verification and validation of quantum computers. So these these were a sequence of papers starting in 2018, but actually the work on these goes back at least 3 years before that. So it took a long time while this work was brewing before the first papers started arriving. So what's the and so what I'd like to do here is to try to get into some of the techniques behind this work. So, to try to see if, to make these techniques actually more widely available. because they can get a little complicated, if you're just trying to read them. So I just want to dip into what the essence of these new techniques is. Okay, so what's the backdrop? Well, we know Hilbert space is exponentially large. We know quantum computers can be exponentially powerful. And so how do we, as classical beings, sitting outside, just able to measure what we can of a quantum state, how can we reach in and verify, validate, the output of a quantum computer, or various aspects of it? So it turns out that one of the key things in doing this is to enforce some sort of a qubit structure on the prover's Hilbert space. So what does it mean to enforce a qubit structure? Well, what it means is actually enforcing a structure that the prover or the quantum computer has to respect in its operations. So what this means is we enforce an initial state on those qubits and the X and Z operators on the qubit. Okay, so let me give you a small overview of what one can do this way. So in this cryptographic leash, we use post-quantum cryptography to help the verifier in this task, in this quest. And post-quantum cryptography meaning crypto systems, which classical crypto systems where you can encrypt, decrypt classically, but where even a quantum computer wouldn't be able to break it. Okay, so in particular, all right. So using these techniques, what we'll see is you can get scalable, efficient proofs of quantumness. A proof that what's behind this black box is really a quantum computer, and that no classical process could have in sub-exponential time, unless it broke the post-quantum cryptography, it couldn't possibly have created the transcript of interaction with the verifier. Certifiable randomness, verification of the output of the quantum computation, fully homomorphic quantum computation, so a way of delegating the quantum computation under encryption to the quantum computer in such a way that the privacy is preserved. And even some part of quantum cryptography. So if you had, quantum key distribution, device-independent quantum key distribution, but now you want to do it using these computational assumptions. Then there's without having to share entanglement. So that there's a way you can do that. Okay. Now, so let me go back to this notion of enforcing qubits. So it turns out that this has played an important role in different settings of what it means to have a verifier interact with the quantum computer. So the first setting in which this was explored was a mildly quantum verifier, not a classical verifier, where the verifier in addition to doing anything, computing anything classical, has a constant number of bits of storage, plus a quantum channel to the prover. So the idea here was that the verifier randomizes his quantum bits using a quantum one-time pad or a Pauli twirl. So you take your quantum state on this one qubit side, and you apply a random X and a random Z operator. Either apply X or not or Z or not, and then you perform your quantum computation under the covers. And the idea here was that because these qubits that the verifier sends to the prover have been encoded in this way, they've been encoded under this quantum one-time pad, the prover really cannot discard the qubits. The prover must respect the integrity of these qubits. Otherwise, the prover cannot possibly carry out will get detected. So this was done by Aronov, Benor, Eban, and Broadbent, Fitzsimmons, Keshefi, or at least proposed there. And it took several years before these proposals were actually proved to achieve what they claimed. The second setting was where you have a classical verifier and two entangled provers. So this is something that we call the classical leash, where you use the entanglement properties of now you have two quantum computers or two provers who are entangled, and you play a bunch of CHSH games to enforce a qubit structure on the internal states of the provers, and you enforce that they apply X and Z operators when they are asked to. So this is something that I did with Ben Reichart and Falk Unger. And then there were a sequence of improvements which were quite dramatic. So in this paper with Reichart and Unger, we had to do polynomial in N CHSH tests to enforce N qubits. So in this follow-up work, Natarajan and Wittig used quantum low degree tests to reduce that number exponentially to just polylog N CHSH tests and polylog N communication. And then, of course, this and work on certified randomness played a role in this beautiful result of Sheen, Natarajan, Wittig, Wright, and Yuen on MIP star equal to RA. Okay, so. All right, so here's an outline of what I'll talk about. So I'll start with a qubit certification protocol based on trapdoor claw-free functions. There's a key piece of this, which is a you need a trapdoor claw-free function with an adaptive hardcore bit, and we can implement this based on learning with errors problem. So I'll describe a little bit about this because this can get a little tricky to understand. I'll show how this can be used to give a scalable and verifiable, efficiently verifiable proof of quantumness. This is the kind of task that that Google called, this is also called quantum supremacy or quantum advantage, and so and then I'll say how this is used. How you can enforce a qubit using Jordan's lemma. And how this leads to the randomness certification protocol. And then I'll touch on, the verification protocol for quantum computation, give you just an idea about this. And if there's time, more efficient randomness protocols and proofs of quantumness without this adaptive hardcore bit. Okay, so So now the key here is in what I'll talk about is using post-quantum cryptography to enhance the power of this verifier. Well, if you are trying to use post-quantum crypto to level the playing field, then this is a little bit tricky. And the reason it's tricky is there's a wrong way of doing this, where you you can use the fact that the verifier is more powerful in this domain of decrypting this cryptography, but you can just use it to cripple the quantum computer, and that's not really very constructive. So the right way of using this quantum cryptography is post-quantum cryptography is to actually let the verifier have that advantage, but still enable the quantum computer to do, to still exercise its unique computational capabilities. And so to do this, one, let me say what sorts of techniques one has to use to actually do this. So the basic protocol that lies at the heart of all this is what we call the qubit certification protocol. So this is based on work with Zvika Brzezinski, Paul Cristiano, Urmila Mahadev and Thomas Wittig. So what this protocol does, after exchanging a couple of rounds of messages, is that the prover ends up with a quantum bit in the state superposition of 0 and 1, where the phase of this qubit depends upon some bit C, classical bit C, and C is equally likely to be 0 and 1. So this qubit is equally likely to be in the plus or minus state, and therefore it's indistinguishable from a completely random qubit. And it is a completely random qubit. Now, even though the prover creates the state, the prover doesn't know whether it's a plus or minus state. And in fact, the prover only knows an encryption of C, which the prover can then transmit to the verifier. And since the verifier can decrypt, the verifier would know whether it's a plus or minus state. So now we have this asymmetry between the prover and verifier, where the prover can create this quantum state and manipulate it. The verifier is classical, cannot do either of those things, but the verifier knows what the quantum state is. Okay, so this turns out to be the basic primitive that one needs to build on. And now let me just say how this primitive is created. So we use what are called trapdoor claw-free functions. So it's a pair of functions, pair of injective functions from say n bits to m bits. They have the same image. So the set of and since they have the same image for if y is in the image, then there must be an x0 and an x1 such that f0 of x0 is equal to f1 of x1 is y. And this is called a claw, right? And these trapdoor claw-free functions have the property that it's very hard to find a claw. But if you have knowledge of the trapdoor, so first this function is easy to compute. So given x, it's very easy to compute f of x. It's very hard to find a claw, two x's that map to the same y. But if you have the trapdoor, you can invert. Given y, you can figure out x, so you can actually figure out x0 and x1 and this entire claw. Okay, so how does this qubit certification protocol work? So the verifier transmits this function, the parameters of these claw-free functions to the prover. So the prover can now compute this function. The verifier, of course, keeps the trapdoor information about these functions secret. Now the prover creates this superposition. Takes a superposition over all x. There's a first register which contains a bit 0 or 1, which it's in a superposition of 0 and 1. And now the prover creates actually computes the value of f of x, f sub b of x, f0 or f1 of x in the third register. Now the prover then measures the third register. This is very similar to Simon's algorithm, right? So the prover now measures the third register to get a value for f of x, which is y, and now the first two registers are in a superposition of 0 x0 plus 1 x1, where x0 and x1 are the pre-images. And now the verifier issues and the prover sends back y, commits to y. Okay, so at this point the prover is holding on to the superposition, and the verifier issues one of two challenges. One is to measure these first two registers in the standard basis, which means that that the prover now responds by sending either x0, x0 or 1, x1. Or the prover or the verifier challenges the prover to provide an equation, which means that the prover measures these two registers in the first and second registers in the Hadamard basis. And so, you know, when the prover measures the second register in the Hadamard basis, then he's left with the first qubit in this state that I promised, which is a superposition of 0 and 1 with a phase of which depends upon the bit C. And then and meanwhile, the measurement of the second registers yields an n-bit string D. Okay, and if he also measures the first qubit in the Hadamard basis, that reveals C. So now, if you look at C, how C relates to D and x0 and x1, then C is exactly D in a product x0 plus x1, where the sum is over F2, or it's bitwise sum mod 2. Okay, so now this is something, of course, that the verifier can check. So because the verifier knows both x0 and x1, and the prover is providing C and D. So this equation down below, that C equal to D times x0 plus x1 is easily checked by the verifier, and that's the qubit certification test. So now, what's the point of this qubit certification test? So first off, this already provides a proof of quantumness. So if the prover can pass these tests, you know, then this provides a proof of quantumness. So now to see this, well, we've already seen that the quantum computer can answer either challenge. Now, because this is using post-quantum cryptography, actually, it turns out that no polynomial time classical or quantum computer can answer both challenges, X and these C and D. And the reason for this is, well, if you can answer both challenges, X and CD, then you can actually compute both pre-images. And this is a property called the adaptive hardcore bit, which I'll talk about in a moment. Okay, but now, assuming that, you know, this statement about this difficulty is actually symmetric for quantum and classical. So, you know, how could one then say that you know, the this black box cannot be a classical computer? So the key idea is that a classical prover can be rewound. So if it can answer either challenge, it can answer both. What I mean by this is, we could run, if this was a classical computer, we could run this protocol all the way through with say a challenge 0, and then we could you know, since it was a classical computer, we could just record its state right after it sent back Y. And then we rewind the classical computer to that state. And this time issue it a challenge 1, and now we have both of the responses, and so we can use those to break the claw-free trapdoor claw-free function. Okay. Okay, so so why is it hard to provide both one pre-image and this equation? So if you look at this equation, well, what does this equation tell us? Well, it gives us some joint information about x0 and x1. In fact, we are taking the bitwise sum of these two strings, so we get an n-bit string, but then we are actually getting only one bit of information about that n-bit string. Which one? Well, it's the bit determined by D, because the inner product of D and this n bit string gives us a bit, right? So it gives us the exclusive or the sum mod 2 of some subset of bits of this x0 plus x1. Okay, so now this is where we have to prove this this new kind of hardcore bit property, that even if you know this one bit of a joint bit of x0 in x1, together with one of the pre-images, either x0 or x1, then you can reconstruct the other bit as well. Okay, so that there's an efficient algorithm to find a claw and therefore break LWE. Now, there's a very important part of this, which is that this is an adaptive hardcore bit, and this is because the adversary, the prover, gets to choose D, which means that the adversary gets to choose which bit we are thinking of as the hardcore bit after seeing the particular trapdoor claw-free function f0 and f1 that's chosen by the verifier. And so we know how to construct this based on learning with errors, and it's based on this very beautiful property of learning with errors called leakage resistance. So let me just say a few words about this. So what's learning with errors? It's this very simple property which says, well, if you're given n linear equations and n unknowns, then you can of course solve these linear equations and figure out what the unknowns were. But now suppose you're given many more than n equations with n unknowns, and except that each of these linear equations is slightly noisy. So for each linear equation, we add in a small amount of noise. So we are going to be working over zq to the n for some large q, and the noise is going to be small compared to q. So it might be 0, 1, 2, or something mod q, whatever it is, some small Gaussian from a suitable. So the entries of E are chosen from some suitable Gaussian. Right? Okay, so now you get to see these many more than n linear equations, but they're noisy. And so what one can show is that, and A is a random matrix, the noise is random, and you can show that that these linear equations are information theoretically more than enough to specify the variables S for secret, uniquely. But the LWE assumption says that it's very hard to solve these equations, and in fact, given A and T, the value of these noisy equations, you really cannot computationally efficiently distinguish them from A and U for a uniformly random U. Right, so you cannot tell, whether these were noisy equations or this was just completely random noise. Okay, okay, so now how do we actually get trapdoor claw-free functions from LWE? Well, you fix an LWE sample, and so the way you specify your functions is by just specifying a single LWE sample. So you have your matrix A and you have T, which is AS plus E for some secret S, right? And now you define F0 of X just to be A times X plus E0. And you define F1 of X to be A times X plus E0 plus this sample T. So now there are two issues. One is the output is no longer, and it's actually a distribution, right? Because E0 is a Gaussian error. So the way to deal with this is just to instead of calling it a trapdoor claw-free function, we'll call it an NTCF, a noisy trapdoor claw-free function. So we'll just live with the fact that the output is being picked from a distribution. Okay, so now the second issue is how do we show it's 2 to 1, and how do we show it's claw-free? So to see this, notice that if E was 0, in this LWE sample we got, then F1 of X is AX plus, well, it's AX plus T. T is A times S, so it's A times X plus S plus E naught, right? So F1 of X is F naught of X plus S. Okay. So it really does end up being 2 to 1 in the way we want, but E is not equal to 0. And so what we do in order to deal with this is we sample E naught from a much wider Gaussian than E was sampled from, so that the distribution for F naught of X plus S and F1 of X are essentially indistinguishable, right, statistically. And so then we get, these two, we have a wider Gaussian and a smaller Gaussian added to it. So the wider Gaussian just spreads out just a little bit and it's almost indistinguishable. And now we do enforce essentially this property, but now we can see that X naught minus X1 is S, which is the LWE secret. So if you can figure out both X naught and X1, then you obviously break LWE. Okay, so now how do we actually create this superposition? We start with X, superposition over all X, 0X plus 1X. We compute, if it's 0, then we compute AX plus E naught in the third register, otherwise AX plus E naught plus T. We measure the third register, and now we are left with a superposition over X naught and X1. Now, the important thing to note here is that all entries are in ZQ, right, of these X naught, X1. And so we use log qubits to represent each of them. Okay, so I'm belaboring these points because, once you get past the high level stuff, you really have to take a little bit of care in all these constructions. Okay, now let me just say what the adaptive hardcore bit means, and I'm not sure whether I'll really go through why there's an adaptive hardcore bit. I was going to, but let me at least say what it means. So the adaptive hardcore bit means here that the knowledge of the pre-image of a single pre-image X naught or X1, plus a better than 50-50 guess for D times X naught plus X1 for any choice of D means that there's an efficient algorithm to break LWE. Now, by the way, D time, X1 is X naught minus S. So you might say, well, this X naught plus X1 is therefore equal to S. And so this is D dot S. But that's not correct, right? Because remember, X naught and X1 are in ZQ to the N. And this is bitwise addition. So this mixing of bitwise and mod Q is really the key to making all this work. This is why you do end up getting the adaptive hardcore bit and so on. All these properties do actually follow from the fact that we are working mod Q. Okay, so but they are also quite a pain because this really makes things much more complex to analyze. So since we now the important thing here is, since we know a pre-image, say X naught, we can use it nevertheless to compute and efficiently compute from D. From D, we can efficiently compute a D prime such that D prime dot S is D, D dot X naught plus X1. Okay, so sorry, in all of this, there's one other fact I should mention, which is sorry, let me go back here. Sorry, so I made a mistake out here. So this was an error. So to using the NTCF to create the superposition, we don't start with a superposition over all X in ZQ to the N. We actually start with a superposition over X over qubits 0 and 1. And so when we do this computation, we start with X just binary strings in superposition, do this computation, and so we end up with X naught and X1 binary strings. Okay, so this is an essential part of what we are doing. So X naught and X1 are still binary strings. D dot X naught plus X1 still makes sense as bitwise addition mod 2. But now when we say x1 equal to x0 minus s, we mean that's true mod q, right? So this interplay of mod 2 and mod q is what makes all this work. And so here what we are saying is, well, given this such a d from the prover, we can compute a d prime efficiently such that d prime dot s is d dot x0 plus x1, where d prime is now binary. So what we want to do is now where d prime. So now we want to show that d prime dot s is a hardcore bit for LWE, which means that given this LWE sample and even a better than 50-50 guess for d prime dot s, we can find the other pre-image. So we are given one of the pre-images, we can actually compute the other pre-image efficiently. So I won't go over how this happens, but now let me just turn to how this, in addition to giving you a proof of randomness, this gives you a certifiable quantum random number generator. So what this means is we are given a black box, which we assume is a quantum computer. It's given to us as a black box because we don't really trust it. It's either we suspect it's uncalibrated, or if you are doing cryptography, we suspect that the person who designed this black box is actually is our adversary. So we are going to assume that this black box may actually be entangled with the adversary. And what we'd like to say is that the output of this black box, which is n bits, and we feed in log n bits into this black box as a seed. We'd like to say that these n bits are certifiably random. Random meaning statistically random, right? And what by this we mean that whatever simple tests we are performing on this box, if it passes those tests, then it's not that in principle it outputs random bits, or some of the strings it outputs are random, or typically it outputs random strings. No, it means that this particular string that it output must have been random, right? That's what we're going to be certifying. And in fact, we'd be certifying not just that, but for cryptographic reasons, we want to certify also that the adversary who is entangled with this black box, shares entanglement, actually does not learn anything about this string. So you see, it could be that the adversary and this black box share entanglement, and the black box just measures those entangled bits, and then of course the adversary knows what those measurements are, the outcomes would be, because it can measure its own bits and reconstruct exactly this randomness. And this would not be of much use in cryptographically, right? So if your adversary knows your randomness. So we really want this to be independent of the adversary. Okay, so how do we do this? Well, what we do is use pick f pseudo randomly. So we use just log n or polylog n bits of randomness to pick f, and we specify that. So that's our LW sample. The prover now commits to y. We send back one of these two challenges, as pre-image or equation, and now we repeat this process, and we use the 0 challenges to generate randomness. So we say, well, whether we got x0 or x1 is actually going to be random. And we use the 1 challenges to keep the device honest. So when do we do the 0 challenges and when the 1 challenges? So we use some of our log n bits of randomness to choose that, and we challenge only once in a while, right? So we don't need many bits of randomness to pick when to challenge. Okay, so now remember that there's pseudo randomness here. So what we are saying is that the output not only gives us pseudo randomness, right? Because what we are saying is, well, if this prover was unable to break the post-quantum crypto during the protocol, which lasts for a short period of time, then in fact, this must produce statistical randomness, not pseudo-randomness, right? And in fact, to show this, we must show that the adversary also does not get any get any information about this randomness. And to show this, we must say, well, the adversary eventually, has infinite computing power, and so this adversary can actually break this pseudo randomness and this post-quantum cryptography. And so but the adversary, of course, doesn't get to choose this interaction. So the prover does that in real time. And so later the adversary gets to analyze all this, and this is not still enough information to actually break the pseudo-randomness. And so to do this, what we show is that the quantum device must effectively be measuring a qubit in the plus state. So in the standard basis, this yields a random bit. In the Hadamard basis, this is the challenge, which is answered more or less deterministically. Okay, so to do this, we must actually reach into the prover's Hilbert space and now characterize the qubit completely. So what we're going to be saying is, if the prover succeeds, then they must have a qubit in the state in the state actually plus, which he measured in the standard basis or the Hadamard basis. Now, the key thing that allows us to do this is that a qubit is defined by two anti-commuting measurements, right? Say X and Z. But here, anti-commuting meaning that they are, the measurements are, the bases are 45 degrees apart, pi by 4 apart. So here we have two measurements. We are measuring whether the equation, and we are measuring whether we got which of the two pre-images we got. And this adaptive hardcore properties tells us that these two measurements are almost completely uncorrelated. And so now we can use this fact that they are almost completely uncorrelated, together with Jordan's lemma, to decompose this Hilbert space as a direct sum of two-dimensional subspaces, and then claim that these measurements must be almost exactly 45 degrees apart in the two different in most of these subspaces. So how does this go? Well, so for Jordan's lemma, we have two projectors P and Q. So they define the two measurements, P and I minus P, and Q and I minus Q. Okay, so when you have two such projectors, Jordan's lemma tells us that we can decompose the Hilbert space into a direct sum of 2D spaces. And what these do is they pair up the eigenvectors of PQP with QPQ. And within this, so these two in each of these two-dimensional spaces, these eigenvectors E and F, they get mapped to each other under P and Q with some and so the interesting thing is this Jordan angle between these two Jordan vectors. And so the fact that we have an adaptive hardcore bit tells us that in most of these Jordan subspaces, the angle is between these two Jordan vectors must be very close to pi by 4. And so we incur only a small error by correcting these angles to pi by 4 in all the subspaces. And so now that all the angles are pi by 4, we can align these subspaces and thereby get a qubit and our X and Z operators. And aligning these subspaces corresponds to some global unit array that we are performing. So up to a unit array change of basis, they're saying that the prover must have had a qubit such that they actually perform X and Z operators on it on demand. Okay, so so I'm running out of time here, so let me just very quickly say a little bit about this beautiful work of Urmila Mahadev and how it built upon all this. This is how to verify an arbitrary quantum computation. So the prover is carrying out an arbitrary quantum computation and wants to convince a classical verifier that who is somewhat skeptical of the quantum computer, either because for calibration issues or noise issues, or maybe they just don't believe that this was they are skeptical that it was really a quantum computer, right? So now this time, so what Mahadev does is, in her protocol, the prover creates a superposition. Now, before in the qubit certification protocol, the prover was always creating a superposition, either plus or minus. So now the prover starts with a quantum bit in the state alpha 0 plus beta 1, and now it goes through the same qubit certification protocol. So sets up a superposition with x0 and x1, right? And now commits to y, the image on the TCF. Okay, so now how does the prover choose this qubit? Well, actually a sequence of qubits, but to be the ground state of a local Hamiltonian with only XX and ZZ terms, and you can choose this so that this encodes the computation to be performed. So if the prover is actually demonstrating that they have the ground state, then that's sort of saying, yeah, I solved the problem of interest. Now the verifier again chooses to perform either the standard or Hadamard basis test, but now because the superposition of this qubit is more general, okay, so now the standard basis test works as normal as in the previous case, but the Hadamard basis test doesn't quite work as well for more general qubits here, but still, if the prover, what can be shown is that if the prover cheats on the Hadamard test, then the prover can cheat, but that would have been equivalent to the prover choosing a different superposition to start with and not cheating on the Hadamard test. So in that sense, since in this protocol the prover is supposed to choose the ground state and only succeeds if the energy of this state is low enough, then there's no incentive for the prover to cheat, because even though they can, it would be equivalent to choosing a different state and not cheating. Okay, so that's the whole idea behind this protocol. Let me just quickly say one more thing, and then I'll just conclude without. There was a sort of a simplification, at least a conceptual simplification of this protocol. So Fitzsimmons and Kashefi had shown that if the verifier can force the quantum device to prepare one of 8 states and can verify, then they can verify arbitrary quantum computation. And the 8 states are these, where instead of plus or minus, you have these 8 roots of unity in this phase out here. And so Georgiou and Vidic actually showed that you can use this, use the qubit certification protocol essentially in that form, but now not using qubits, but qubits using F8 instead of the Hadamard for the Fourier transform. And they actually had to use quantum random access codes to prove rigidity in this case, and then once they did that, they could just rely on the Fitzsimmons-Kasheffi protocol. So I'm going to skip the proof of quantumness without adaptive hardcore bit and efficiently certifiable randomness, where you get n bits of randomness with a very simple variant of the qubit certification protocol. And let me just say that in conclusion that there's something very there's a bit of a there's a lot bit of a revolution at this intersection of post-quantum crypto and quantum cryptography, both through this style of work that I showed you here, where you use post-quantum cryptography to reach into Hilbert space, and that's there are many further results beyond the ones that I even alluded to here on that. But then there's a whole re-examination of post-quantum, post-quantum crypto and whether what you can do in the presence of a quantum adversary once you have quantum protocols. So there's a lot of excitement and a lot of interest in this area. So I think I'll stop there. Thank you.
Thank you very much for the presentation. Do we have any questions from the audience here live? Any from online? I guess I can ask one thing. What are the implications of being able to prove this with a classical computer? And we just heard about, okay, so when this gets into a regime where it's really hard to probe that quantum computer, what are the implications when we are in that supremacy regime? And will this methodology scale to a point where we can still use classical computers to attractively prove quantumness, even in large regimes of computers?
Yeah, no, very good question. So yes, indeed, the whole point of this is to get these proofs of quantumness well beyond what we could call the Goldilocks regime, where it's 50 qubits or 50 or 60 qubits, where you have a plausible chance of classical simulation, where you can sort of say, well, heuristically or something, at least you can, or you can actually do a classical simulation and show you achieve quantum supremacy. So, for example, with the thing that I actually skipped, this proofs of quantumness without the adaptive hardcore bit. So that gives you the possibility of maybe potentially another way of doing these protocols, which might be more which could be more efficient under certain circumstances. And so there's now a proof of concept implementation on an ion trap quantum computer of these, not yet at the level where you can assert that cryptographic security must be broken, but still it's it's saying that one can start seeing these results both for this and the LWE based protocol. And so there's work being done on, well, what's the minimum number of qubits you need? Right now it's somewhere between 1,000 and 2,000, but it's plausible that one could get that number down to something smaller in the couple of hundred, few hundred range. So that would be as far as proofs of quantumness go. And then of course there are these other applications, having to do with verification or with delegation and so on, which of course I think that there's a lot of work to be done still on these protocols towards making them super efficient, and of course there's a lot of work to be done yet on the hardware side in terms of scaling up the machines to the sizes where these could be implemented. But it's it's certainly there's there's been just a flurry of papers about, both in terms of new applications of these ideas, but also in terms of making these more and more efficient.
Thank you very much. Appreciate it. Warm round of applause.
Thank you.
We'll have a short break, about 5 minutes, and then we'll get to the next session. Thank you very much. Yep, to Zoom.
Oh, you're on.
I entered, yeah, as a speaker. And he emailed me the link, so that once you're in there, you just present from Zoom wirelessly. This has or through the Wi-Fi. Yeah, the Wi-Fi is free. Here, you just go to URI. Yeah, it's a little bit flaky today. It's free stuff or whatever. Or you can go through LTE. Worst case, I guess you could email it. They can use their laptop.